states.
Yeah, something like
You
that.
can switch one as it.
Yeah.
No, this
Oh, this one. Yeah. Cool.
this on the
Thank you.
top.
Yeah, yeah, yeah. Thanks. Okay, so I wanted to split it like this so you could have an idea with what's actually involved in doing a calculation, and sort of play around with things and get used to the ideas involved before saying a few more kind of specific things about kind of technical points about the analysis. So I suppose most of this is going to be about background poles, which is the point where most of you have now got to, and some bits about fitting. So some of you have tried fitting already and have probably come to the conclusion that it takes a long time and sometimes it doesn't really help. So you need to have quite a good starting set before you actually perform a fit, and I'll say some things about Minuit. And then some brief stuff about errors. So in principle, you can use Minuit to generate parameter errors for all the parameters in the fit. So hopefully with tutorial so far, you've managed to set up some particle pairs and add states to the compound nucleus, and used this to identify, with the data, to identify spins and parities of those two resonances. So hopefully you found there's a 1- state and a 4+ state, and you've sort of got an intuitive feel for when you say what the width of a resonance is, what it looks like in terms of the shape, and how that depends on spins and parities. And you might have been able to fit the widths and energies of these things to experimental data. So what I want to say is something about background resonances, and then some examples of fitting with Minuit. Oh yeah, and say something about sensitivity to the R matrix radius parameter in this particular example of carbon-12 alpha-alpha, and something briefly on the sorts of error analysis you can do with Minuit. So this is what we've got. This is the context of what we've got. This is oxygen 16, and the green bit is the bit that we're interested in, right? We have our threshold is here, and the states that we're actually looking at in the calculations, this 9.585 MeV state, which is a 1-, and this 4+ state, right? These are those two states that you see in the calculation. And there are some other states in here that you might be starting to pick up if you started to look at the higher energy data that's also available in the folders. But there's all this stuff above here, right? I mean, our calculation is stopping here, and our data stops here, but there are literally hundreds of resonances above, okay? And you've also been adding all these high energy states in, and to some extent, well, one reason they're there is to make sure you've got all the proper hard sphere components in, and one reason is that later on you might want to use them as a background pole, right? So there is all this strength up here, and the tails of these resonances will be kind of penetrating down into the region that we're interested in. And basically the technique is to say, well, we've got all this strength up here. For all the 0+ states, we're going to lump it all into one resonance and put that at, say, 15 MeV, which is reasonably above the energy range that we're interested in. So the tails of that resonance are basically constant in the region, constant in terms of the R matrix contribution in the region that we're interested in. And for each of the spin parities, we can consider a background resonance somewhere up here that contributes down at lower energies. And then you may be starting to see some effects of that in the calculations. So up here at 15 MeV, we've got a 0+ state, a 0, well, in this case, not a 0- state because it won't contribute because there's no way of coupling carbon-12 plus alpha to get into 0-. Same with a 1+ and a 2-, but in general, we have states of all spin parities up there to account for the background tails of these higher energy resonances. So as I say, we've got an infinite expansion in principle, and in principle there's an infinite number of levels, but we condense all that high energy stuff into one single resonance and to simulate the tails of those resonances. And in principle, background poles can be used to do other things. So not only is it higher lying resonances that you're not including in the fit, but in principle there could be non-compound nucleus direct mechanisms that have a very constant contribution to the R matrix in the region that you're interested in that you can simulate with an appropriate background pole. And in scattering, you can sort of simulate corrections to this hard sphere phase shift, which is not quite like the phase shift that you'd get if you calculated it in a more realistic potential model. So background poles often, when you're looking at elastic scattering, tend to be stronger because you need to account for the fact that this hard sphere is quite a stark approximation for what is actually kind of a much softer interaction. And generally, for reaction channels, you usually only need a few spin parity background resonances. The contribution is usually less significant, but it's a very case-dependent thing. So some cases, they'll be more important than others. And for scattering, you might need all of them. And in general, in principle, you should try all of the spin parities, right? But sometimes it's obvious in a reaction channel where there is interference with a particular resonance. Obviously, it may be obvious that the interference of that resonance is not quite right. So it must be interfering with something coming from a background contribution. So that's what they're for, and you've some experience of how you might put them into a calculation. So hopefully some of you have got to this sort of stage, right? This is the thing that you've all been looking at. There is this 1 minus state here, which has got a width of about 400 keV, and there's 4 plus state here, which is something like 30 keV wide. And this is probably the best sort of fit you can get. So if we take our simplest possible assumption that we have no background poles other than them being there to get the hard spheres right, and you say we've got this state, and they have some width, and you fit using Minuit, this is about as good as you can do. And some of you have noticed that what you get is a really good fit apart from this region up here. So at the highest energy end, there is this discrepancy between the best fit for the calculation and the data, right? And you can ask yourself why. Well, it may be that there are other resonances here, and the tails of these resonances are contributing, and this is actually, the reason there is a discrepancy is there is something missing in the calculation up here. And it may be over here, or it may be over here, but there is something that's not quite there. And if you look at the data, that's what you see. So some of you started looking at this higher energy data, and you see there are all sorts of resonances over here. And this one in particular, which is rather close to the data that we're actually looking at, could probably be a background for this that's causing this discrepancy here. Okay, so this is possibly the main contribution to this background, right? There is actually a specific state. We can attribute our background pole really to a specific state that's causing this discrepancy. The other thing to note, and this is probably an added complication that you won't want to deal with this afternoon with these data, if you're fitting this green data, which some of you started to do, you start to hit other particle separation thresholds. So at this point here, which is something like 4.3 MeV in the center of mass, so I don't know, it's just below 12 MeV probably, the alpha 1 threshold opens up. So this is the final particle pair in this case is a carbon-12 in an excited state, a 2+ state, and an alpha particle. So this is, in principle, after this point, the states may have significant widths in this channel, right? And that, in principle, could change the fits. And also up here, around about 5 MeV in the central mass, 12.1 MeV-ish, the proton separation threshold opens up. And there are certainly particular resonances about 6 MeV. I think there is a state, a 1- state that does have a significant proton width, right? And in principle, to take these things into account, you need to go back to your particles pairs tab and add another particle pair in, right? And once you've done that, you can, for these states, add in widths for the protons, and it will take it all properly into account. And in principle, the best thing to do is also then to fit, say, nitrogen 15 pp, right? So you've got extra constraint on those proton widths. But for now, don't worry about that. I mean, for the most part, you can assume that the widths of these resonances above these thresholds are just the alpha particle widths, and you'll get something reasonably close. So we think this resonance is maybe the background contribution that is causing this discrepancy here. So what we can do is look in the data tables. So many of you have done this already, but we see our 1- state, and it's got a width of 420 keV, and our 4+ state, which has got 26 keV. And if you plug these numbers in, you get something that looks very much like the fit that or the calculation that I just showed. And so I should have put this on as excitation energy, but this state here is about 4.3 MeV. So 8.67 plus 4.3. Oh no, that's just not the excitation. So the alpha separation threshold is 7.1 MeV plus 4.3 is what? 11.4 MeV. So we should be looking for a state about 11.4 MeV-ish. That may be the background. That may be this state here. Okay. So if we do that, there is this state here at 3 minus MeV that has an 800 keV width. So in general, what we're looking for is states with wide widths, right? If it's a background pole contributing, or if it's a background resonance contributing at lower energies, its width must be reasonably wide, okay? And if we look up here, there is this 0 plus state that claims to have a width of 2.5 MeV, but its spin parity assignment is tenuous and it's even got a question mark above its energy. So I would ignore this one for now because I suspect it's a bit dubious and it's not really evident from the data that this is present. But there is this wide 3 minus resonance. So what we can do is, if we take our calculation, if we just continue to fit our lower energy data, ignoring that higher energy data, we can include that specific background pole as a 3 minus background pole. So this is the calculation without any background poles at all. And then if we assume that there is one background pole and it has 3 minus, which is probably somehow associated with that near 3 minus state, the fit improves a bit. So you can see you get the magnitude around this resonance quite a lot better. This is just one angle in particular, obviously. So there is some improvement around here. But when you allow for all background poles, you get an even better agreement. So all we're doing here is all those high energy states of 15 MeV, we're giving them some small width and allowing Minuit to fit their widths as it pleases, right? And gradually that improves the agreement with the data. So if this is only the energy region you're interested in, you can just include those background poles and they'll have some relatively arbitrary width. The relative strengths for the different spins and parities might tell you something about indicating specific states that may be contributing, but you're probably not worried about that. You're just worried about getting a better fit to this data set. And including all those background poles up to, I think this one up to the 5 minus, gives you this very good fit. So another thing that I wanted to say is about the sensitivity to the R matrix radius. So Pierre has said that, well, and I've said that in principle the calculations, the results of the calculations should be insensitive to this R matrix radius. Certainly your formal parameters, so the reduced width amplitudes and the pole energies will change. They will be sensitive to the reduced width amplitude. But the cross-section itself and the observed type widths, so once we've converted our internal formal reduced width amplitudes to observed widths, they should be relatively insensitive to the radius. And you can see what we get here. So this is just a fit to the carbon data that you've all been looking at with that 4 plus and the 1 minus resonance. And with no background poles, you see this is the total chi-squared as a function of the R matrix radius. And you can see this is very much dependent on what the R matrix radius is. Okay, so it's got a nice, well, sort of parabolic type minimum with a minimum somewhere at 3 MeVs, 3 femtometers. So this is a sensible sort of distance for being outside the range of the nuclear interaction, or the interaction of the sort of central nuclear potential. But you can see there is this distinct minimum. Okay, and so we know that if we include that 3 minus state, we're taking account of that state that's just above our data. So maybe that accounts for most of the background that we see. And if we include that 3 minus state and do the same thing, calculating at different radius parameters doing the fit, you still see this distinct minimum. And the center of the minimum shifts a little bit. Firstly, the chi-squared is a lot lower, right? So including this 3 minus background pole actually makes a very big difference to the chi-squared. It goes down by more than a factor of 2. But you still see that it depends very strongly on what the R matrix parameter is. Okay, and in principle it shouldn't, right? If we have a complete calculation, we shouldn't have this dependence on the R matrix radius. So what we can do is, instead of just including the 3 minus background, if we include background contributions for all different spin parities, what we get is this. So at low radius radii, it's very similar, just a 3 minus background, but at higher radii, once we've included all the possible background contributions and let Minuit fit them as it pleases, what we get something that's basically insensitive to this R matrix radius, as we should expect it would be. And And I'd not done this calculation before last week, but it's neat how it turns out that it's really very robustly insensitive to the radius once you're taking into account all the possible background contributions and all those possible tails and accounting for all sorts of things. And so this, if we work out naively what our radius should be, if 1.5 times the cube roots of the mass is, we get about 5.3. And once we get to about 5.3, we are basically insensitive to this radius. So smaller than this, we might expect that the radius is too small. And there you would never expect to get the same. You would never expect below that radius to be insensitive to what it is because it's just too small for the system.
Is that 2 to the third or 4 to the third?
That's a good question. It should be 4 to the third. Whether or not this value is 4 to the third or 2 to the third, I'm not sure. But okay, so if it's 4 to the third, I mean, certainly the radius, you would expect the R matrix radius to be somewhere, I mean, the minimum to be somewhere in this region. And yeah, and at this point it's doing okay, and if you go too small, it's hitting a block. But we can also look at the observed type parameters that come out of the calculation. So you might not have looked at these yet, but in that output subdirectory that you specify, there's a file called parameters.out that contains the observed widths after the fit. And you can see that for this sort of range of R matrix radii from 5 to 6 MeV, the energies change a little bit and the widths change a little bit, but basically they're relatively insensitive to the radius for both states. And this is what we should probably expect. So this is something you should check, really. It's particular. I mean, that you need so many background poles is probably particular to scattering, but even if you're doing a reaction case, P alpha, alpha P or something, you should check. So fitting. Some of you have started to do fits already, and you may have found that it takes a long time and it doesn't necessarily give you a sensible result. Maybe. You need to have very good starting parameters, right? Minuit is not smart in the sense that it doesn't understand if you have an energy, what it means by an energy, right? I mean, we can all see that if we look at something like this, right, and we know this state has an energy, and we know if we change the energy, it's going to shift this resonance to the left or the right, depending on how we change it. So we can see by eye, if we have a curve that goes like this, you know, up here, then if we increase that energy, it will improve the fit in a particular way. But Minuit doesn't understand that. It just has a list of parameters and it varies them somewhat arbitrarily according to sort of gradients in the chi-squared to obtain what it thinks is the best fit. So it's not necessarily very smart. It's very effective at optimizing parameters, but you need to put it very much in the right sort of local minimum before you use fits, because it'll take a long time. And if you're just sat watching a fit and it comes out with rubbish at the end, then there's not much point in doing it. You can optimize it much better by doing it by hand. So you really need to have kind of the essential elements of the fit in place before you bother to start running Minuit. So you need the spins and parities established, and the energies and the rough widths, and ideally the interferences. So it's not such a big issue in elastic scattering, but in reaction channels, you need to understand what the interferences are, where the interferences between different resonances are coming in. And at that point, you can say, well, Minuit can fit it. So you should start simple and gradually build up the calculation until you fit. And Minuit is just fitting on minimizing this chi-squared function, which is just the difference between the theoretical and experimental value squared divided by the error squared. And so now I have a couple of videos which show, yeah, it's the first for us, which show Minuit fitting, right? So this is something you're all familiar with, right? This is our calculation, and this is our starting parameters, right? And these starting parameters are kind of deliberately crap. They're the right spins and parities, but the widths are obviously kind of wrong, and the energies are kind of wrong. And you could all see, right? If we just shift this down a bit and make it wider, and shift this down a bit and make it narrower, you'd get a really good starting fit, right? But what this shows is the Minuit calculation output for every single iteration. So you can see exactly what Minuit is doing as it performs the fit, right? And it doesn't do much. It sort of twitches a bit. And you can see the iteration count. So it's taken 200 iterations, and suddenly it jumps, right? And suddenly it's quite close. And at this point, we're up to 300 iterations, and you could have got to this by eye in about 5 seconds, right? And it's still going. So Minuit spends a lot of time twitching, adjusting very small differences. And gradually it gets to where it goes. I think there's a background poll in here as well. But now we're up to 700 iterations and it's still going. So it'll keep going till it decides that things aren't changing. But that takes a long time. And it's still going. Okay, then it finishes, right? So that sort of, you could have got a much better agreement quickly by doing it yourself, doing it by hand, right? Which is something you should do. So, right, notice, so I've got another video, and it's basically the same thing. So, but I've just changed the starting parameters. So this is a particular set of reasonably bad starting parameters. And this is another set of particularly bad starting parameters. I've changed this first resonance. This first resonance is exactly the same, but I've just shifted this one down a bit and reduced the width a little bit, right? And it's going to do exactly the same thing. So it's going to fit. And we'll see what happens. Right. So again, it twitches, and it's adjusting some background pole and adjusting these widths. And then at some point, this will probably jump into the right place. There you go. But it gets this wrong, right? It gets into a local minimum. It decides that the width of this should be basically 0, and it gets stuck. Right. So we've got to about 400, 500 iterations, and there's no way it can get from here to getting that resonance in the right place. And it wasn't that far off, right? It wasn't as, I mean, it was about as far as off as it was in the other case. It was just on the other side, and it gets stuck in a local minimum. So this is a sort of, you know, genuine local minimum that you've got into because the starting parameters just weren't quite good enough. So I mean, you understand things, right? You understand how the bits of the fit build together, and you fitting by eye is much more effective than letting Minuit do it with ill-constrained parameters. That's that one again. Okay, so there's one final one. So this is the higher energy data that some of you might have started to look at. Some of you were having trouble finding good starting parameters. It's obviously possible because I managed to do it, but I don't know offhand what they were. But I can look that up. And so this is just going to do the same thing. So there's a lot more resonance, far more resonances here. The starting parameters are pretty good. But the frame rate is increased by a factor of 10. So this is just going to show every 10 iterations. So it's going a lot faster, but it takes a long time, right? If you see, it starts at 10, and the starting parameters are pretty good. But you can see it's doing various things as it goes along, and we're already up to 2,000 iterations, right? And it's not. And it's okay. So at this point, it's looking pretty good at 3,000 iterations, and it just keeps going. It keeps going and twitching things until it eventually is satisfied. So with this data set, oh, that's not the wrong thing to press. This one. Yeah. So it may be, I mean, there's all sorts of odd structure over here where things are interfering, right? And whether this sort of thing is very well constrained by this particular data set is not clear, right? So the energy resolution of this data isn't great. So it may be that it's not really good enough to constrain very precisely all the resonances that are in that region. And this data isn't too bad. So Minuit is good at fitting once you have something very well set up. But you've got to have it well set up to start with, and you've got to have a sort of intuitive understanding of what's going on. And that's what you'll spend most of your time if you ever do any R matrix fitting. So briefly, Philomena mentioned this last week, I think, or the week before even, just about parameter errors. So Minuit can be used to establish what the errors on the fit parameters are. And basically, after fitting, you have an optimal set of P parameters that we'll call this P0, and you can tailor expand the chi-squared about this minimum. So if you have, for an arbitrary set of parameters near that minimum, you can expand it in terms of the chi-squared at the minimum and this second derivative matrix, basically. So it's the derivatives of the chi-squared with respect to the parameters and differences of whatever the parameter value is relative to the minimum. Okay, and from this, Minuit will do this, and it will. I could use this, couldn't I? From this H, you can to get a one sigma variation in the probability that your fit is correct, you effectively increase the chi-squared above the minimum value of 1. So by varying the parameters, Minuit can establish effectively a kind of multi-dimensional surface in the chi-squared in terms of the parameters where this is true, and from that you get that this derivative matrix times these differences should be equal to 1. So all in all, this will combine. This will establish the parameter surfaces where that chi-square variance is 1, and from that you can establish what the errors of the parameters are. So this is all done internally, and it will just spit out a file that tells you what the errors are. And after that, you can define parameter correlations. So this variance matrix is related to the inverse of this H, and then this correlation parameter tells you the correlation between two parameters. So if you've got two parameters I and j, this thing is 1 if those two are perfectly correlated, and less than 1 if they're not. And most often, these are quite small in the calculations that you do, but it's useful for establishing maybe where a certain part of your fit is not very well constrained by the data that you've got. And so if you do one of the options when you're running on the Calculate tab where you can calculate by data or do Minuit fit, there's one of these options is a minus error analysis. And this will output stuff to output/covariance matrix.out. And in there you'll find a list of parameters and this correlation matrix. So the list of parameters, so this was again for carbon-12 alpha. You have your 9.5 MeV or 1 minus state, this 3 minus background pole, and the 4 plus state, and each of these parameters is numbered, and these are the fitted values. And you have the correlation matrix that tells you the correlations between the two parameters. So the diagonal elements are all 1, and then the off-diagonal elements tell you about the correlations. So this is the biggest off-diagonal element, 0.49, which tells you that the energy of the 9.5 MeV state and its width are relatively loosely correlated. So you can, if you adjust the energy of that state, you can compensate the deficit in the fall or the increase in the chi-squared by adjusting the width slightly, right? But 0.5 is a relatively weak correlation. But there's more. Philomena's lectures give you some references to look at if you're interested in that sort of stuff. So there's lots of things that you can do with Azure that I haven't mentioned. You can do capture reactions, so you can include both the internal and external part of capture. So the internal part, you just have a regular resonance with a channel, and you set its gamma gamma, which is the width for the internal part, and the external part you can include by putting the final state in as a level and specifying the A and C of that state. And there are experimental effects that can be taken into account. So this data for carbon-12 alpha shows probably some effects from the target or from the non-monoenergetic nature of the beam. So in principle, you can take these into account. So you can do beam convolution, you can have a Gaussian distribution of the incident energies, you can do target integration over the thickness of the target. And all of this can be done on a per segment basis. So if you have different data sets that have different experimental effects, you can take that into account for each set independently. And also, if you're interested in astrophysics, you can also calculate reaction rates. So based on your R matrix calculation, you can then do a calculation for an astrophysical reaction rate convolving your R matrix distribution with some temperature distribution or some variety of temperature distributions to calculate the overall reaction rate as a function of temperature in a star, say, which apparently takes quite a long time, but I've not used it an awful lot. So just a summary of phenomenological R matrix fitting provides one method to understand structure of nuclei at low excitations, and it provides a means to calculate cross-sections for places where you can't measure it, right? Either in astrophysics or materials or other applications. Ideally, your calculations should begin as simply as possible. You should build them up from the stuff that is obvious in your energy range, so the broad resonances or the narrow resonances, stuff that you can see and define by hand what the parameters should be. Gradually building it up. Once you have something that has a reasonable description of the cross-section, you can then perform a fit with Minuit. Yeah, and in principle, the R matrix fit that you get should be weakly dependent on the radius, but you should probably check. You may need to include additional background contributions to account for that. So that's it. Feel free to carry on with the tutorial, and if anybody's got different reactions that they want to look at and want to ask about how you do the analysis or advice on setting them up, then by all means do. I'm happy to help. That's about it.
You had Ed, at some point you had a green data set and a red data set. Those are just two experimental outputs with
Yeah,
errors on the
here.
Is that right?
Yeah, these are just two different data sets. So the angles, they're at slightly different angles, which is partly why there's this sort of shift. But this red data set is, I mean, you've got both of these in the folders, right? So this is that Radovich data set, and this is from Feng, I think, is the author.
So because they're different angles, the parameters for those two are much more similar than the data might indicate. The fitted parameters.
Yes, the fitted, I mean, yeah, so I think, I forget exactly. I think one is 150 and one is 165 degrees. But yeah, so you can see there's a difference in the calculations, right? So there's this difference in the data, but there's also this difference in the calculations. So that they are closer than they look.
You could fit the red points and then with your parameters calculate 165 or whatever the angle is and compare directly with the previous.
Yes, you could if you wanted to, yeah. Yeah, and it should give you, I mean, you can see in the region that they overlap, they're actually pretty close. I mean, these data points are a lot closer than a lot of data sets. So, yeah, when you're doing nuclear astrophysics and your error bars are this big and only one person has ever measured it and it's over there, then it's easy to say that your data sets agree, right? But with data like this, in the material science community, one of their big problems is that the data sets are just inconsistent. Like, I mean, came across an example, proton scattering on boron 11, that was published in the early 2000s, and there is a 20% systematic error in the data, right? So this is pretty good. These were probably the better data sets that I could find where there was some overlap and they actually agree. But yeah, that's something you need to be careful, just picking data sets from literature, particularly if you're getting from X4 or some online database. You do need to check, you need to look at the original papers to look at target effects, so to check those sorts of things. Very often with X4, you need to go back to the paper to check exactly what's given, because X4 doesn't always specify whether it's center of mass or lab. So if you've got differential cross-section, that's quite important. And sometimes it doesn't even specify whether the energy is central mass or lab. So X4 is useful for getting a data set, but you actually need to look at the paper to look at what actually is in the data set. It's because it's not always clear. And there are all sorts of data sets, and in principle you should include everything, but you need to sort of apply some common sense and actually try and understand what's going on with individual sets to do things sensibly. But I'm happy to answer any questions anybody's got. Otherwise, feel free to carry on and ask when you want some help. Oh.